So in the previous class, I started discussing about the special cases in two-dimensional collisions. I have already discussed the special case one in the last part of the previous class. So now I'm going to show you the notes for the special case one. So those who are writing the notes, come on, get ready with your notebook and pen. First, I will show you the conclusion which I have discussed in the special case one. First, I am going to show you the conclusion of the special case one, which I have discussed in the previous class, so that you can first copy the conclusion. Next, I will show you the working for this conclusion, which I have also already discussed in the previous class. Come on, look at the screen. The ball collides elastically with a fixed plane, and if the surfaces in contact are smooth, then the ball rebounds with the same speed and at the same angle with the normal to the plane. That's the conclusion. First, you copy down this conclusion. Next, I am going to give you the working for the conclusion. I'll be showing the diagram in my next slide. First, you copy this conclusion. Next, for working, you can write working here. Let U and V denote the magnitudes of the velocities of the ball just before and just after impact with the smooth plane. Come on, finish writing the notes up to here. In case you need more time to copy the working, you can take a pause and take your time to copy the working. I am going to show you the continuation. I am going to show you the notes for the continuation for the working of this conclusion. So here I have shown the figure. Here U is the magnitude of the U bar is the, in vector form, U bar is the initial loss of the ball or smooth sphere. Just before it makes a collision with a smooth and fixed plane, and this theta is the angle with the initial loss U bar makes with the normal to the plane. V bar is the velocity of the ball just after impact with the fixed smooth plane, which is directed at an angle alpha with the normal to the plane. Sometimes theta is called angle of incidence and alpha is called angle of reflection. Can resolve this initial loss to U bar into rectangular components in the tangential direction and normal direction. That means can resolve the initial loss to U bar into rectangular components in the direction tangential to the smooth plane with which it collides and in the direction normal to the smooth plane. The U bar makes an angle theta with the vertical direction here. The component of U bar which is tangential to the smooth plane will have magnitude U sin theta. The component of U bar which acts normal to the smooth plane will have magnitude U cos theta, but it acts downwards. So I consider the collision between the ball and the smooth plane. So the ball is the first body and plane is the second body. U1n is the component of initial loss of the ball in the direction normal to the plane. So if you give positive sign for components of velocity along the normal to the plane and away from the plane in the upward direction, you have to give negative sign for component of velocity toward the plane. So I have written U1n as minus U cos theta. As explained earlier, the surfaces in contact are smooth. then no force acts on the ball in the tangential direction during the time of collision. Therefore, the moment of the ball in the tangential direction remains same. So mass of the ball can be assumed to be constant. Therefore, component of velocity of the ball in the tangential direction remains same. The velocity v bar can also be resolved into two rectangular components along the normal to the plane and tangential to the plane. The component v cos alpha acts along the normal to the plane. The component v sin alpha acts tangential to the plane. In my next slide, I will show the diagram showing the components of v bar. So the component of v bar in the tangential direction after collision is v sin alpha. So the component of velocity of the ball in the tangential direction before collision is u sin theta. So the component of velocity of the ball in the tangential direction, that is the direction tangential to the plane, remains unchanged. So you can write v sin alpha equal to u sin theta. In the normal direction, you can use the equation for coefficient of restitution, which looks similar to the equation I have discussed in one-dimensional collisions. So in a one-dimensional collision, you can write E equal to V2 minus V1 by U1 minus U2. In the similar way, for normal direction, you can write E equal to V2n minus V1n divided by U1n minus U2n. So U1n and U2n are the components of initial velocities of the two bodies in the normal direction before collision. V1n and V2n denote the components of the final velocities of M1 and M2 in the normal direction just after collision. Here the ball is the first body and the smooth plane or fixed plane which with the ball collides we consider as second body. Here the plane which with the ball collides is fixed. So before collision and after collision, the velocity of the plane is 0. That means U2 is 0 and V2 is 0. So you can write V2n equal to 0 and U2n also equal to 0. So you get E equal to minus V1n by U1n. Here you can write similar way. This small u you write here instead of capital U, because you better follow same notation throughout. Instead of capital U, you write small u here in the denominator. Your notes. So you can copy down this. So you can write V1n equal to minus E times U1n. Here U1n is the component of initial velocity of the ball before collision with the smooth plane in the normal direction, which is minus u cos theta because directed opposite to the component V sin alpha. V1n is the component of final velocity of the ball in the normal direction after collision. That can be written as V cos alpha. So you can substitute V1n equal to V cos alpha and U1n equal to minus u cos theta. So you get V cos alpha equal to EU cos theta. Come on, you copy down this working up to here, including the diagrams. Including the diagrams, you copy down the whole working. So in case you need more time to copy this working, probably you need more time to copy the working, you can take a pause and take your own time. So I am going to show the continuation for this. So we can divide the equation 1 with equation 2. On the left hand side, if you divide V sin alpha with V cos alpha, you get V gets cancelled. You get sin alpha by cos alpha tan alpha. On the right hand side of the equation, you divide u sin theta with EU cos theta. Sin theta by cos theta you can write as tan theta. So here on the right side, I have shown the diagram showing the components of velocity v bar of the ball just after impact with the plane along the tangential direction, normal direction. The component of velocity of the ball in the tangential direction is v sin alpha. The component of velocity of the ball in the normal direction is v cos alpha. So if you divide the equation 1 with equation 2, you get v sin alpha by v cos alpha equal to u sin theta by u cos theta. So on the left hand side v gets cancelled, on the right hand side u gets cancelled. So you get tan alpha equal to 1 by e times tan theta. So if the collision is perfectly elastic, then E equal to 1. So if you put E equal to 1, you get from first equation or from the concluded tan alpha, you get tan theta or alpha equal to theta. And in the first equation, if you substitute alpha equal to theta, first equation is v sin alpha equal to u sin theta. So if alpha equal to theta, then sin alpha will be equal to sin theta. So you get v equal to u, which I have written directly here. That means if the collision of the ball with the smooth and fixed plane is perfectly elastic, the ball rebounds with the same speed with which it strikes the smooth plane and also the same angle theta with the normal to the plane. So there is one more conclusion I wanted to discuss which I have not mentioned in my previous class. Suppose this also can write, if the collision of the ball completely inelastic, the collision of the ball with the plane is completely inelastic, then can write E equal to 0. So if the collision of the ball with the plane is given to be completely inelastic, then E equal to 0. If you substitute E equal to 0 here, so tan alpha equal to 1 by E, that is 1 by 0 into tan theta, that is 1 by 0 into infinity, or alpha equal to pi by 2, or means alpha is 90 degrees, pi by 2 radian or 90 degrees. So from, or otherwise from second equation also you can see. From first equation, v sin alpha equal to u sin theta. We take alpha equal to 90 degrees on the left hand side of the first equation. V sin alpha becomes v sin 90 degrees or v equal to u sin theta. But with the velocity of the ball after the collision will be equal to the tangential component. That means, try to show you the situation roughly in the diagram. The same diagram which I have drawn earlier. Here the ball strikes the smooth and fixed plane with initial velocity u bar at an angle theta with a normal to the plane. The collision is perfectly elastic, then the ball rebounds with the same speed with which strike the plane and rebound and at same angle with the normal to the plane. But if the collision is completely inelastic, then alpha will be 90 degrees and v will be u sin theta. That means after the collision, the ball moves along the plane, tangential to the plane, with the velocity equal to the tangential velocity. Only tangential velocity exists. Velocity in the normal direction becomes 0 after the collision. That means after the collision, the ball moves along the smooth floor with velocity of magnitude u sin theta in the tangential direction, and there is no velocity in the normal direction, so it does not rebound from the floor, moves along the floor. Alpha is 90 degrees. So that will situation. So those are writing the notes, please finish copying the notes up to here, including what I have written manually on the right side. So in case you need more time to copy this, you can take a pause and take your time. Next, I am going to discuss the second special case. But I will be discussing the second special case. But you, after copying up to here, you stop writing. I will be just giving the explanation. I am going to give you the explanation for special case 2. But I will show you the notes later. First, you listen to the explanation. You can copy the notes later. So, I am going to discuss next another special case. I call it case 2 in two-dimensional collisions. Please stop writing now. You just concentrate only to listen. I will give you the notes for this case 2 also separately next after the discussion. So I consider the case of collision between two colliding masses, two bodies of same mass with smooth surfaces, and the collision is perfectly elastic but not one-dimensional. As discussed in the past, in the case of head-on or one-dimensional collision, suppose if the second body is initially at rest, if you consider the case of one-dimensional or head-on collision between two smooth solid spheres, two uniform solid spheres, so the second body is initially at rest. In the initial velocity, the first sphere is directed along the line joining the centers of mass of the two spheres. If the initial velocity first sphere is direct along the line joining the centers of the two uniform spheres, then the collision will be head-on or one-dimensional, because the impulsive force on M2 by M1 during the time of collision acts along the line joining the centers of the two balls, means in the direction of U1. Then the collision will be head-on. So in the case of head-on or one-dimensional elastic collision, the two second body which is initially at rest has same mass as that of the first body. Then after collision, as explained, the first body will come to rest and second body will begin to move with the velocity of, with the original velocity of the first body. This is what I have already discussed in the past in the case of one-dimensional collisions. Because the part of the discussion in case 2 will be similar to this case. Now I am considering the collision between two smooth spheres, two identical smooth spheres of same mass, or two spheres of same mass, but the initial velocity of the first sphere is not directed along the line joining their centers. Suppose the initial velocity of the first sphere is directed at some angle denoted by alpha, with the line joining the centers of the two spheres. That means the collision in this case is elastic but not one-dimensional, because initial velocity u bar of the first sphere before the collision is not direct along the line joining the centers of the two spheres. That means I am considering the case of oblique or two-dimensional collision, which is perfectly elastic between two spheres of same mass, and second mass is initially at rest. So I would like to give you the explanation that after the collision, I would like to give you the proofs that after the collision, I would like to show that the two masses move in mutually perpendicular directions after the collision. So here, applying conservation of momentum, that is vector sum of linear momenta of the two colliding masses after the collision is equal to vector sum of the initial momenta of the two colliding masses before the collision. So m1 v1 bar plus m2 v2 bar equal to m1 u1 bar plus m2 u2 bar. Here u2 is 0, u1 bar can be written as equal to u bar, which represents the initial mass of first body before collision. And m1 equal to m2, let us suppose denote the mass of each body by m. So mv1 bar plus mv2 bar equal to mu bar plus second term becomes 0 on the right side. So if we divide the equation with mass m, you can write v1 bar plus v2 bar equal to u bar. Now we take mod both sides. Then we square the modulus, that is square of the modulus of resultant of v1 bar and v2 bar, that equals square of the modulus of v bar. As we studied earlier in vectors, if vector mod of a bar plus b bar is root of a square plus b square plus 2ab cos theta, where theta is the angle between the vectors a bar and b bar. That means in the parallelogram law of addition of vectors, square of the magnitude of the vector sum of a bar and b bar, having square of the magnitude of vector sum of two vectors a bar and b bar is given by mod of a bar square of mod of a bar plus b bar equal to f square plus b square plus 2ab cos theta. So using that formula here, the square of the magnitude of the vector sum of v1 bar and v2 bar, you can write v1 square plus v2 square plus 2v1 v2 cos theta. The right side you can write as u square. You call this as equation number 1. Please don't write running notes when I am discussing. I will show you the notes in a more systematic way after this discussion. Then you can copy the notes. Please don't write the notes at present. Now if the collision is perfectly elastic, then the total kinetic energy of the two colliding masses just after collision can be taken to be same as the total kinetic energy of the two colliding masses just before collision. So the initial kinetic of the first mass is equal to half m1 u1 square. m1 equal to m here, u1 equal to u. Initial kinetic of second mass is 0. The final kinetic of the first mass you can write half m1 v1 square. Final kinetic of second mass you can write half m2 v2 square. Here m2 equal to m, m1 equal to m. So you get u square equal to v1 square plus v2 square. We'll substitute the value of u square from second equation into the first equation. So from the equations 1 and 2, substitute this value of u square from equation 2 on the right hand side of equation 1. You get v1 square plus v2 square plus 2v1 v2 cos theta equal to u square. You can write v1 square plus v2 square. So if you v1 square plus v2 square gets cancelled on both sides, you get 2v1 v2 cos theta equal to 0. The collision is perfectly elastic. So from equation 1, 2, you can say that none of the two quantities v1 or v2 can become 0 here when the two bodies have same mass. Therefore, cos theta must be 0. Here theta is the angle between the two vectors v1 bar and v2 bar. So cos theta equal to 0, with theta equal to 90 degrees. That means after the collision, the angle between the velocities of v1, two colliding masses becomes 90 degrees. That means after the collision, the two colliding masses move in mutually perpendicular directions. So, if a smooth solid sphere makes a head-on, oblique, not head-on, oblique elastic collision with another stationary solid sphere of same mass, then after the collision, the two colliding masses move in mutually perpendicular directions. You can arrive at the same conclusion by using the discussion I have done earlier. Earlier I have discussed the collision between two smooth solid spheres. In the case of collision between two smooth solid spheres or between two smooth spheres with uniform distribution of masses, so the center of mass of each sphere coincides with the center of that sphere. Then, as I told you, the surfaces in contact during the time of collision are smooth, and the component velocity of each sphere in the tangential direction remains same. And in the normal direction, for velocities in the normal direction, the collision can be regarded like a one-dimensional collision. So here, in the case of one-dimensional elastic collision, as I discussed in the past, that if the two colliding bodies have same mass and second body is initially at rest, then after the collision, the first body comes to the second body, takes the velocity of the first body. That means the second body starts moving with the original velocity of the first body. The similar reasoning can be used here for normal direction. Here, in the normal direction, so here in the case of one-dimensional elastic collision, the two colliding bodies have same mass. Then we write V1 equal to U2 and V2 equal to U1. We discussed in the past. Similarly, in the normal direction, here two colliding masses have same mass and collision perfectly elastic. Therefore, you can write V1N equal to U2N and V2N equal to U1N. So U1N is a component of initial mass of the first sphere in the normal direction after the collision, which is equal to U cos alpha in the figure I have shown. And U2N is a component of initial mass second sphere in the normal direction before collision. Before collision, second sphere is at rest. So initial mass second sphere in the normal direction becomes 0. That means the velocity of M1 in the normal direction becomes 0 after the collision. But velocity of M1 in the tangential direction after collision will be same as its initial velocity in the tangential direction before collision. So V1T is the final velocity of M1 in the tangential direction after collision. U1T is the component of initial velocity of M1 in the tangential direction before collision. That will be equal to U sin alpha. That means after the collision, the first sphere will have no velocity in the normal direction, but it will have velocity U sin alpha in the tangential direction. And final velocity of second sphere in the tangential direction after collision must be same as its initial velocity in the tangential direction before collision. Initial velocity second sphere before collision is 0. That means after the collision, the second sphere has no velocity in the tangential direction. So for these directions, I have shown this is the direction of initial velocity per sphere before collision, which makes an angle alpha with a line joining the two spheres. I am drawing the diagram in a different way. So initial velocity per sphere makes an angle alpha with the line joining centers of two spheres, and two spheres have same mass here. Collision is elastic. Then after collision, the first sphere will have no velocity in the normal direction. So after the collision, the first sphere will move in the tangential direction. So velocity per sphere after collision is same as equal to the velocity in the tangential direction, that is u sin alpha. But second sphere after collision moves in the normal direction. That means in the normal direction, the velocity of the first sphere will be in the tangential direction. So this should be taken as v2 here. v2 will be u cos alpha. Second sphere will have velocity in the normal. This is the normal direction. That is, first sphere will have velocity equal to the final loss of a sphere after collision will be equal to its initial velocity in the tangential direction. That is u sin alpha. That means after the collision, the first sphere moves with velocity of magnitude u sin alpha in the direction tangential to the two spheres to the points of contact at the time of collision. And second sphere moves in the normal direction with velocity of magnitude cos alpha. That means after collision, the two spheres move in mutually perpendicular directions. Next, I am going to show the notes for the same case 2. Now you get ready again with your pen and notebook. I am going to show you the notes for same case 2. First, I will show you the conclusion, which you can copy the conclusion. Better remember the conclusion so that you can answer some of the objective questions related to this case faster. Now look at the screen here. Look at the screen here. Case 2. I have shown the conclusion on the screen. An uniform sphere or ball makes an elastic oblique collision with an identical sphere which is initially at rest, such that the surfaces which come into contact are smooth. Then after the collision, the two spheres move in mutually perpendicular directions. Come on, copy down this conclusion. And better remember this conclusion so that you can, if you use this conclusion, you can answer some of the questions faster. In case you need more time to copy this conclusion, you can take a pause and take your time. I am going to show you the continuation for this. So I am going to show the working for the conclusion. From momentum conservation, connect m1 u1 bar plus m2 u2 bar equal m1 v1 bar plus m2 v2 bar. Here m2 equal m1 equal to m. Let us suppose and u2 is 0 and u1 equal to u. Therefore, if you substitute u2 equal to 0, m1 equal to n, m2 equal to m, u1 equal to u, get mu bar equal to m into v1 bar plus m into v2 bar. If you divide the equation with m, we get u bar equal to v1 bar plus v2 bar. Squaring both sides, you get u square equal to square of the magnitude vector sum of v1 bar and v2 bar. Come on, all of you first finish copying the notes up to this step. If you finish writing the notes up to this step, then I can show you the continuation for this on the screen. So in case you need more time, we take a pause and copy this working. Next, I am going to show the continuation for this. So you can write square of magnitude of v1 bar plus v2 bar. You can write v1 square plus v2 square plus 2v1 v2 cos theta. Theta is the angle between v1 bar and v2 bar. We call this equation 1. As the collision is elastic, you can write sum of the final kinetic energies of the two spheres or two bodies after collision is equal to total initial kinetic of system. So initial kinetic of the first body is half mu square. Initial kinetic of second body is 0 because second body is initial at rest. So final kinetic energy of first body after collision is half mv1 square. Final kinetic energy of second body after collision is half mv2 square. So total kinetic energy of the two colliding bodies after collision will be half mv1 square plus half mv2 square. which can be equated to the total initial kinetic energy before collision. The collision is perfectly elastic. Divide the equation with mass m, or can half m is the common factor gets cancelled both sides. You get v1 square plus v2 square equal to u square. Now substitute the value of u square from second equation into the first equation. So combine equating the values of u square from equations 1 and 2, you can write v1 square plus v2 square plus 2v1 v2 cos theta equal to v1 square plus v2 square. Come on, finish writing the notes till this step. So you can cancel v1 square plus v2 square on both sides of the equation. You get 2v1 v2 cos theta equal to 0. So next I am going to show you the working continuation for this, notes for continuation. In case you need more time to copy this, you can take a pause. So 2v1 v2 cos theta equal to 0 you get, or cos theta equal to 0, or you get theta equal to 90 degrees. Come on, finish copying up to here. In case you need more time to copy this working, you can take a pause and take your time. I have shown the diagram showing the situation of case 2. That means here, m1 is the mass of the first body which is initially in motion. U is the magnitude of initial of the first sphere before collision, which makes some angle alpha with the line joining the centers of the two spheres. The mass m2 of second sphere is same as the mass m1 of first sphere. Second sphere is initially at rest. So after the collision, as I discussed previously, for normal direction, you can consider the collision to be one-dimensional elastic collision. That means when you analyze the components of velocities in the normal direction, you can treat the collision like one dimension along the normal direction. So in the case of one-dimensional elastic collision, if the second sphere which is initially at rest has same mass as the first sphere, then after collision, the first sphere in motion will come to rest and second sphere will start moving with the velocity of first sphere. That means after the collision, the velocity of m1 in the normal direction becomes 0. So it retains only its velocity in the tangential direction. So component of velocity of m1 in the tangential direction before collision is u sin alpha. So v1 equal to u1 t equal to u sin alpha. The velocity of m1 in the normal direction becomes 0 after collision. And velocity of m2 in the normal direction after collision, same as the initial velocity of m1 in the normal direction before collision, which is equal to u cos alpha. That means after collision, m2 moves with velocity of magnitude u cos alpha in the direction normal to the surface of two spheres or along the line joining the centers of two spheres before collision. Okay. Then after the collision, first sphere will have no velocity in the normal direction, it moves in the tangential direction with velocity of magnitude sin alpha. If you want to copy this diagram, you can take a pause and copy this diagram. So I am going to show one problem based on one of these special cases. If you finish writing after this. In case you need more time to copy the diagram, you can take a pause and take your time. See the problem here, small particle traveling with velocity v collides elastically with spherical body of equal mass and of radius small r initially kept at rest. The center of the spherical body is located distance r by 2 away from the direction of the motion of the particle. Find the velocities of the two particles. Of course, your answer should be in terms of v. Here r is the diagram should be drawn more clearly, definitely. So this radius of this sphere is r. Make the sphere larger than what I have shown in the diagram, so that the direction of the motion of the first particle, small particle, makes an angle, is at a distance r by 2 from this reference line. So r by 2 should be less than r, is it right? So I try to show the diagram on the right side. I will discuss the solution of this problem now. So I have tried to show the situation roughly on the diagram. This is the particle which is moving with velocity of magnitude v, so that the line of direction of the velocity v of the particle before collision is at a perpendicular distance r by 2 from this horizontal line. That alpha denote the angle which with this velocity v bar of the particle, initial velocity v bar of the first particle before collision makes with the normal direction. That means the direction normal to the surface of sphere through the point of contact at the time of collision. So you have a right angle triangle here. The length of hypotenuse side equal to r, that is the radius of sphere. This distance equal to r by 2. So sin alpha you can write r by 2 divided by r, opposite side of hypotenuse, r 1 by 2. So you get alpha equal to 30 degrees. So the velocity of the first particle acts at an angle alpha with the line normal to the surface of sphere. So component of initial of the first particle in the normal direction, which we denote by u1n, is equal to v cos alpha. The component of velocity of the first particle in the tangential direction before collision will be written as v sin alpha. As I discuss here, this problem concerns special case 2. The two particles have same mass, so after collision they move in mutually perpendicular directions. So along the normal direction, the collision can be treated like one-dimensional collision. As I discussed earlier, in the case of one-dimensional elastic collision, the second body is initially at rest. Then after collision, the first body in motion will stop and second body starts moving with the velocity of the first body. That means the final velocity of the second sphere, second particle in the normal direction, same as the initial velocity of the first particle in the normal direction, which is equal to v cos alpha. The final velocity of the first particle in the normal direction, same as the initial velocity of the second particle in the normal direction. Second particle is sphere, which is initial at rest. So after the collision, the velocity of the first particle in the normal direction becomes 0. Therefore, after the but velocity in the tangential direction remains same. So in the tangential direction, as I told you, when the surface is in contact or smooth, the velocity in the tangential direction remains unchanged. So final velocity of the first body in the tangential direction is equal to initial velocity in the tangential direction, that is u1t, equal to v1t otherwise. u1t is v sin alpha. And final velocity of the second sphere in the tangential direction, same as its initial velocity in the tangential direction. Before collision, that is 0. That means after the collision, the sphere will have no velocity in the tangential direction. That means in this direction. So after the collision, the sphere moves in this direction with velocity of magnitude v sine alpha. Sine alpha equal to 1 by 2. So it will be v by 2. And the particle moves in this direction. Velocity of the particle in the normal direction becomes 0. Of velocity of the first particle. The normal direction becomes 0 after collision. So velocity of first particle after collision, same as its velocity in the tangential direction. So this should be written v2 actually. This should be taken as v cos alpha. v2 equal to v cos alpha. That is v cos alpha is v cos 30 degrees. V cos 30 degrees. So v2 finally can write, but v root 3 by 2. And v1 equal to v sine alpha. Sine alpha is 1 by 2. So v by 2. So finally the answers are v by 2 and v root 3 by 2. That means after the collision, the first particle moves in this direction, tangential to the point of contact during that. In the direction tangential to the sphere through the point of contact of the particle with the sphere. And after collision, the sphere moves in this direction, that is along the normal to the surface, initial position surface of sphere, like this. So after collision, the magnetic velocity of the first particle v by 2 and magnetic velocity of the sphere is v root 3 by 2. If you want to copy the solution of the problem, you can copy the solution of the problem. You can take a pause and copy the solution.